We're going to look at the reduction of an aldehyde or a ketone with sodium borohydride or lithium aluminum hydride. Just to be clear, sodium borohydride is only able to reduce aldehydes and ketones to alcohols, but lithium aluminum hydride can reduce aldehydes, ketones, carboxylic acids, esters, amides, you name it. It can reduce it because it's a much stronger reducing agent. And the reason for the differences between the borohydride and the aluminum hydride is aluminum prefers to be less negative than the boron because it's further down in the periodic table in that column, so it's more reactive for that reason. Now what you're going to have is an aldehyde or a ketone. I'm just going to put two R groups on here because it doesn't matter if these are hydrogens or carbon chains. If you're dealing with lithium aluminum hydride, these may also be ester groups or amide groups or alcohol groups to make it a carboxylic acid. It can be a variety of different things. It could even be a halogen. You could have an acyl chloride. But if you are using sodium borohydride, the sodium is just a spectator ion. It does nothing except balance charge here. And then you have your borohydride. Now in 351, we talked about boron chemistry before. If you remember back to some general chemistry, you should remember that boron prefers to make 3 bonds, and it does this very well, but there's no reason why it can't have 4 bonds in an octet. But boron is perfectly happy with 3, and the reason for that is boron has 3 valence electrons. And so it usually pairs up those 3 valence electrons and you have an empty p orbital. So it tends to be a very good electron pair acceptor. And in this case, when you have it with sodium and another hydrogen, it forms sodium borohydride. And it has accepted those electrons from the hydrogen. Now, as you think about these boron-hydrogen bonds, in terms of electronegativity, boron has an electronegativity of 2.0, and hydrogen has an electronegativity of 2.1. So hydrogen is actually slightly more electronegative, and it will actually be the one that takes this pair of electrons when a bond breaks. So hydrogen is going to be the nucleophile. This isn't any different than any other nucleophile you've seen reacting with the carbonyl group. You're going to see this over and over and over again. But hydrogen will be the negatively charged species. You're going to have a hydride here. And it will be attracted to the most positive carbon over here on the aldehyde or ketone. And that will be the carbonyl carbon. And if you can't remember that, take a look at the oxidation numbers. Whether these R groups are carbon or hydrogen, you will or will not give those electrons to the carbon, but the oxygen that's making the double bond to the carbon would be assigned both of those electrons. So whatever you do, this carbon is going to have a positive oxidation number, so it should want electrons, and it's going to accept those electrons from the hydride. So that will be able to dump electrons onto the carbon. Now, carbon doesn't want 10 electrons, so a bond has to break, and the weakest of the bonds that it has is the pi bond to the oxygen. So oxygen is going to accept those electrons. Now, as it is accepting these electrons, it's going to take electrons and form a bond to the boron. So you can draw it this way, or you can do it a little bit differently. One other thing you can do is to show this electrons forming the bond to the boron. Either way, perfectly acceptable. You can show the pi bond breaking, which is actually what I like to do. And this pair of electrons, one of the lone pairs going to the boron. The point is, oxygen is acting as an electron pair donor to the boron. So as you continue on, you make a tetrahedral intermediate. And you're going to see lots and lots of these. What's going to happen is this complex can react with 3 more aldehydes or ketones, whatever it is you've got in the solution, because there are 3 more hydrogens on the boron. And I'm not going to show this, but it's basically a repeat of this step 3 more times. Okay? So at the end of all of that, I'm going to call these R primes because they're not quite the same R as I have down below. These R primes are exactly the same as this. This is what is equal to an R prime. There are 4 of these around the boron. Okay? And it will stay like this for a moment in time. Now, in the case of sodium borohydride, you usually use the solvent water, and as a result of that, it will continue to react. If you try to do this, though, with lithium aluminum hydride, you'd have an explosion. When you use lithium aluminum hydride, the solvent you would use in the first step is always something like diethyl ether because it's so much more reactive. So with lithium aluminum hydride, this is where you'd stay. So in place of the boron, you would have an aluminum, and it would stay there. And then in step 2, you would very slowly add water, and it would be drop by drop by drop, because the water would be so reactive with the complex. So this is going to be very reactive with water. And we're going to draw in our water right now so that we can use it. But here's your solvent. Now, again, we've talked about boron not being able to make up its mind about which oxygen it wants to pair up with, and it again has the exact same issue here. We're going to break some bonds. What bond we're going to break is this boron-oxygen bond here, and oxygen being the more electronegative atom will take those electrons when a reaction occurs, and it will use those electrons to form an oxygen-hydrogen bond. As that happens, hydrogen can't form 2 bonds, so those pair of electrons are given to the oxygen, and as oxygen gains more electron density, it will dump electrons onto the boron. So this looks very similar, if you remember, to the second step of hydroboration oxidation when you do the oxidation step. This is very similar to that as you break apart the complex. So what you get as a result of all of that are these 2 chemical species. So we have been able to create the alcohol we were intending. Now, this hydrogen right here was the one that was initially bound to the boron. And they know that it came on as a hydride. And this hydrogen comes from the solvent, the one here in red. So they come from different places, and they know this. They've done labeling experiments. It's very clear which hydrogen comes from which place. This remaining complex here, the boron complex, will go through this process 3 more times, okay, so that in the end, we have a total of 4 of these alcohols that we're interested in. That's the equivalence ratio.